Hey guys, welcome to the only guide you'll ever need to fully understand lift mechanics.
Today we're going to cover 3 scenarios when the lift is at rest or constant velocity, when it's accelerating upwards, and
when it's accelerating downwards. Now,
let's start by defining the forces involved. We're going to assume we have 2 boxes. Box A, the yellow one, that is stacked on top of box B, the red one, inside the lift, as you can tell. Since these objects are stacked, they're in contact, which means they exert reaction forces on each other. That's the basics. Now, we're going to look at box A first.
So everything has a mass, and if all those things are close to another massive thing, those things are also going to have weight.
So you have the weight of A that is acting downwards, and since A is sitting on B, box B will exert an upward reaction force on A. Now these are the only 2 forces acting on box A. Now this is crucial. We're going to bring in Newton's third law here. You should know that the reaction forces are always Newton's third law pairs. Since box B exerted a force upon box A is going to exert a force on box B in the opposite direction, downwards, with the exact same magnitude. We'll call this the reaction from A, okay? Now, let's focus on box B. We have the downward reaction force from A we just discovered. Now box B has its own weight as well. So far, we have 2 forces on B that are acting downwards. Now, there must be a balance to that force, right? Now, since B is touching the floor of the lift will exert an upward reaction force on B to hold it up. Okay, now everything's balanced. Well, it depends if it's at rest or if it's actually accelerating. We'll get to that in a moment. Moving to the lift itself. Now, because the lift pushes up on B, B will push down on the lift. Again, a third law pair. Now, the lift has its own weight as well, acting downwards. To counteract these downward forces on the lift, we have the cable attached to the top. This cable is what exerts an upward force we call tension. Okay? Now, quick note is that if a question says the lift or scale pan is light, you assume the mass is 0. But here we're including the weight as well. You're going to find it in different questions, okay? All right, moving on to case 1, rest or constant velocity. Now that we have our diagram, let's move to case 1, where the lift is at rest or moving at constant velocity. The most important thing to remember here is Newton's second law. If we are at rest or constant velocity, acceleration is 0. And if acceleration is 0, the resultant force is 0. Please do not memorize the equations that I've written here. Just look at your diagram and apply logic. The total upward forces must equal the total downward forces on each of the different individual objects, okay? So for box A, the upward force equals the downward force, so the reaction from B will be equal to the weight of A. It has to be. Otherwise, it's not going to be balanced. And for box B, the upward force equals the total downward forces. So the reaction from the lift will have to equate the addition of the weight of B and the reaction from A that is exerted on B. That's for the first case. That's literally it. Simple, right? Now, why don't we consider the lift only? And we resolve in either direction, up or down. Then we know that the lift has its own weight, so it's going to act downwards, obviously, and we're going to have a reaction force exerted by B. Because the lift also exerted a reaction force on B, as we've seen before. These 2 are the only downward forces on the lift, and to counter that, we need another force, and that force is what the cable provides at the top. The cable is exerting a reaction force on the lift that is acting upwards. There's like a hook in the cable that connects the lift, okay? Now, we call that tension, as you can see here, just because it's a cable. You can see in other places as well in mechanics where whenever there is a string, cable, tow bar, light rod, whatever, we always call it tension, where in reality, when it is actually connected to another object and the string is supposed to exert a force on the object, that force is always going to be the reaction force instead of the tension. We just say it's tension because the tension throughout the string or cable or whatever just happens to be equal to the reaction force that it exerts on the lift. You have to know that. Isn't that important? They wouldn't ask you about this, but I feel like it's good to know. It's going to help you in physics as well. Okay, we're done with the lift. We just found out that the weight plus the reaction will be equal to T. All right, now what if we take the whole system? If we take the whole system and resolve up or down, since it is at rest, the direction doesn't matter, then simply we can just say that all the upward forces in the whole system will be equal to all the downward forces, right? So what I mean by that is the reaction from B plus the reaction from the lift plus the tension, these are all forces that are in the upward direction. These forces are going to be equal to the sum of all the downward forces, which is the weight, the three weights of A, B, and the lift, and the reaction from B and reaction from A. All right, so we can see the final equation after canceling all of them out. We can cancel them because they're all equal. The reaction forces, the pairs are equal. And you can also call them internal forces, as I've mentioned here, you can see. And in the end, we just get tension is equal to the three weights. That's what happens. So that's it for case 1. We're going to move to case 2 now. You can see for A, resolving upwards this time because we're accelerating upwards. We're moving upwards. Okay, hence we're going to take up as the positive direction. And if we do that, then notice the forces on A, forces that are acting on A. We've got the reaction from B upwards, and downwards we have the weight. So it's going to be R from B minus WA is equal to mass times the acceleration. And keep in mind again, the mass is of A only, not any other mass. All right. If you move on to B, the same thing. We're just going to look at the forces that are being exerted on box B, which is the reaction from the lift acting upwards minus reaction from A minus the weight. We add the minus because they're in the opposite direction, to which we took positive. Equal to the mass times acceleration. Quite easy. We're just using the formula resultant force is equal to mass times acceleration. Just in case 1, we just had acceleration equal to 0, which basically meant that the resultant force would have to be 0, as in the total upward forces will have to be equal to the total downward forces. Okay. For case 2, of course, we have a non-zero acceleration because we're actually accelerating. All right, and if we consider the lift only in case 2 and resolve upwards, we're going to have, of course, the tension because tension is pointing upwards, and tension minus the weight of the lift minus the reaction that is being exerted on the lift by B equal to mass times acceleration. And again, mass is of the lift. Now, when we take the whole system, as you can see here, and we resolve upwards, we're kind of doing the same thing that we did in case 1, except now we're keeping all the forces to the left because the right-hand side is not 0 anymore. We have non-zero acceleration. So you can see that all the upward forces here, I've written them first, tension plus R from B plus R from lift minus all the weights and the reaction forces that are downwards. This is for the whole system. We're going to take into account all the forces that are acting on the system. Okay, and if we do that, the mass that we take in this equation is, of course, going to be the mass of the whole system. So, which is why you can see that I've added 3 m's here. I've color coded them as well, so you know the mass of A, B, and the lift. All right, and then again, we can cancel out the reaction forces that are equal, and we're left with tension minus the weight minus weight minus weight equal to the 3 masses multiplied by the acceleration. Quite easy. You don't have to memorize this formula. It all should make sense. Okay, now we're going to move on to case 3 now, where we accelerate downwards. So now we're moving downwards. And keep in mind, we have positive and negative acceleration, as in just to show if you're decelerating or accelerating, it doesn't really matter because, well, if it is decelerating, the acceleration would just come out negative. That's the only difference. Okay, so if you're moving downwards, of course, we're going to resolve downwards. We're going to take downwards as positive. If we do that, then for A, we're going to have the weight first as positive, and then we minus R from B. Okay, and that equal to mass times acceleration. Same for B as well. Weight plus reaction from A minus the reaction from lift, because the reaction from lift is acting up, equal to the mass of B times acceleration. Now for lift, we resolve downwards again. We have the weight and the reaction from B, and then minus the tension, equal to the mass of the lift times the acceleration, as you can see. And then finally, if we take the whole system and resolve downwards, we're going to do the same thing that we did in case 2, except now all the downward forces are going to be positive because we're taking downward as positive, and the upwards are going to be negative. Okay, so weight plus R from A plus WB plus W lift plus R from B minus reaction from B minus reaction from lift. And then we can, of course, cancel them out. Again, all the reaction forces are just canceled out all the time because they're internal forces, as I've already mentioned before. And of course, again, we add all the masses up and multiply that with acceleration, and we're left with the final formula here. WA plus WB plus W lift minus tension is equal to the 3 masses multiplied by the acceleration. I hope all that was really clear. If you have any questions, comment down below. I will be happy to help out, and I'll see you in the next one.